speaking a little bit about chemical reactions, right? We've spoken about rates of reactions. We've already always also spoken about energy change that occurs during a chemical reaction. So in a typical chemical reaction, normally you have your reacting substances. Let's call them reactants. And essentially, these reacting substances will produce a product, right? So maybe we can have chemical A plus chemical B, which in turn produces chemical C plus chemical D. You can have a number of products or reactants, right? Cool. But there's also a chance that sometimes what happens is that these products here turn into or are converted back into reactants. So you might have a situation such as this where C plus D now forms A plus B. So we're having your product being converted back into reactants. And there's particular terminology that we use to describe some of these effects. So in this instant, we would call this the forward reaction, right? Where reactants produces are used up to produce products. So we call it a forward reaction. In this case, where products are converted back into reactants, we would say this is the reverse reaction. Right. Cool. So let us take a sort of a more practical example. Let's say we have a reaction between carbon dioxide plus water, and we form H2CO3, right? And we call this our forward reaction. But then it can also happen where H2CO3 is broken down back into carbon dioxide plus H2O, right? Cool. So, but then there's also a way in which we write this particular equation or this particular reaction, because in this reaction whereby reactants can form products, but also the product can form back into reactants, we call that a reversible reaction, right? So you see it's a reversible. I don't know where my other board is. Reversible. I'm feeling a bit tired today. It's a reversible reaction, right? And we know when we write a reversible reaction, this is what we would write. For, let's say in this instant, we would actually say it is carbon dioxide, CO2 plus H2O, and then you just write, you use that arrow over there like that, and then which will form H2CO3. But because it's reversible, the process can also go back. So we'll draw this line like this. This is to indicate that it is a reversible reaction. So let me repeat myself again. It's a reaction where a reversible reaction is a reaction in which reactants can be used up to produce products. However, products can also be converted back into reactants, right? Cool. And we've spoken a little bit about rates of reaction, right? So an important thing is that there's an important thing that you should know when the rate of forward reaction will equal the rate of let me write reaction there, will equal the rate of reverse reaction. So when they're equal, and you'll see we'll speak much more about what this actually means. So when that happens, we say that our chemical reaction is in a state of equilibrium. So it's very important for you to be able to define what we mean when we say a reaction is in a state of equilibrium. It's a point in time when the rate of the forward reaction equals the rate of the reverse reaction. So let us actually draw, just to kind of make this point clear of equilibrium, let us draw a graph. Okay, so let us draw a graph to kind of further explain this concept of equilibrium when the rate of the forward reaction is actually equals to the rate of the reverse reaction, right? So we'll just have your normal x and y axis, right? And let's say on your x-axis, you just be time. Doesn't matter, it can be in seconds or in minutes. Let us say it is in seconds, right? And then on your y-axis, then you'll have the rate of this reaction. And remember, the equation that we're looking at is this equation. It's where we have carbon dioxide plus H2O that forms H2CO3. It's a reversible reaction because H2CO3 can also form back into carbon dioxide and water, right? Cool. So to draw the forward reaction in this instant, so our forward reaction in this instant would be CO2 plus H2O, H2CO3. So let me just write, it's our forward reaction. And then our reverse reaction would just be H2CO3, which it breaks into carbon dioxide and water. So this will be our reverse. Cool. So we can agree that at the beginning, we have a lot of carbon dioxide and water, right? And then at the beginning, there is not any product. For the forward reaction, there is not really any product, right? So we have, so the rate of reaction in this instant, it starts off very high for our forward reaction, and then it drops up until it reaches a point where it's just constant, right? We can say the same thing for reactant for the for the reverse reaction. It increases, and then at a certain point it reaches a point where it is just constant. And I think you can already see that at maybe from this point onwards, this reaction has reached equilibrium. Remember, this is the rate of reaction, equilibrium. Because at this point in time, the rate of the forward reaction, so this is the forward reaction, equals, so this is the reverse, equals the rate of the reverse reaction. At this point, their rates are the same. So let's say the rate there was 10 something. I'm just putting a number there. You find that here at this point, their rates are actually equal. And at that point, we say that our reaction has reached equilibrium. So forward reaction, we had CO2 plus H2O, which formed H2CO3. Reverse reaction, we had H2CO3, which broke into CO2 plus H2O. Right? Cool. So let us try to kind of further explain this graph because it's important for you to be able to what is it, to analyze it, to interpret it. So at first, let's say at a time initially at the beginning, the rate of the forward reaction is very high. So it's very high. This is an increasing rate of reaction. And then after a while, this rate decreases because more product is being formed, right? H2CO3 is being formed, right? So the rate decreases up until it gets to this point where it reaches a constant phase, right? a constant rate, not phase. So when it reaches here, I want you to be careful. It doesn't mean that there are no more products in your, there are no more reactants in your, no, the reactants are still there. But what happens is that they, if you were looking at this, maybe you were looking at this reaction, maybe you in a beaker, you wouldn't really observe any change. But then it doesn't mean that there are no reactants in your chemical reaction. But now let us take the case of the reverse reaction. So at the beginning, the reverse reaction, there is no product at all, right? So the rate of the reverse reaction is very low. And then it increases, that rate increases as more reaction is being, as more product is being formed. The rate of the reverse reaction increases as, because it's a reversal, more product is being formed, and as a result, product is being broken back into reactants. So that rate increases as well up until it reaches this equilibrium point. And then at this point, these two reactions have the same rate of reaction, and we say that they have reached their chemical equilibrium, right? So just understand that. I'm hoping that I've explained it in a way that you can actually understand or interpret a certain graph. If you're given a graph, for you to be able to say what is happening here, what was happening here, and what was happening over there, right? Cool. So to kind of continue our discussion, let us say you were in a lab. Okay, you don't have to be in a lab, but then let's say you had a beaker. Okay, so you had a beaker, and then inside your beaker, you put in a little bit of water. So there's the water. So there's H2O in here, right? Then you took another beaker, a second beaker, you put water into it. There's H2O in here. But for this beaker, you also placed perhaps a metal, a glass on top of it to kind of seal your beaker. So your beaker is like closed, right? In this instant, it's not closed. And then you measured the water content. So maybe you found that maybe this is 50 milliliters initially, the volume. Same here, initially it was 50 milliliters. And then you went outside, put both of your beakers out into the sun, and then just left them there for like a day. So after a day, you come back and you measure your, so day after a day. So after a day, you come back and you measure the volume. And what you notice is that in this beaker, perhaps now your volume has decreased to, the volume of water has now decreased to about, let's say 20 milliliters, right? But for this beaker that has a closed thingy and lid on top, you find that it's more or less at 50 milliliters. And I'm sure you can already predict what happened in there. So remember, let's call this beaker A, let's call this one B. So in A, you have a process whereby as a result of heat, your water, your liquid is going to evaporate, right? So you have evaporation because of the heat, right? So it evaporates and it evaporates out into the atmosphere, right? The same thing is still happening here. We still have evaporation. It evaporates, but then it doesn't actually go into the environment. That evaporation is turned back into liquid. So meaning when we have or gas turned back into liquid, we have condensation. So in this beaker here, the rate of evaporation is equals to the rate of condensation. So as more water is evaporated as a result of heat, it is also condensed back into liquid. Hence, when you measure it after a day, you still have 50 milliliters. Nothing has changed. No, the volume of the water hasn't changed. So in beaker A, we had what we call an open system. And in beaker 2, we have what we commonly refer to as a closed system. And you have to be able to differentiate between the two. So, what is a closed system? What is an open system? Let us start there. What an open system is a system that is continuously interacting with the environment, the same way that the evaporated water was just going out into the environment, right? And then a closed system in reverse is a system that is isolated from its surroundings. So this system is isolated from the surroundings by just putting this glass on top of your beaker, right? In this instant, matter, which is our water and energy, can flow into and out of our glass beaker, right? True. And then so the beaker can be heated or cooled down, and then that is a change in energy. And then water vapor can also come out, which is our matter. And then in this instant, um the energy can enter or leave the system, so you can either heat this beaker or cool it down. However, water, that evaporation doesn't actually is not able to leave because our system is closed. So it's very important for you to be able to distinguish between a closed system as well as what we refer to as an open system. And this actually brings us to the closure of this lesson.